So, and the second point for this part is related to the source of the errors. So, actually, the main source of the errors, it seems to be a little bit strange, but it comes from the incorrect determination of the area of the solar cell. Actually, it doesn't mean that you cannot correctly measure the size, the geometry. It's something more complicated, because actually the main problem is that you have to define correctly the photoactive area of your solar cell. There are some examples. For instance, if you have a crystalline silicon-based solar cell with heterojunction solar cell with amorphous-originated emitter, in the most cases you can neglect the lateral conductance of the emitter, because it's quite small. It's really quite small, and you can define the real surface of your solar cell by the transparent conductive oxide, for example, ITO layer. So, for example, if it's the solar cell and this blue, it's ITO, so we can suppose that the real area of your, the photoactive area of your solar cell, it just corresponds to the surface of the ITO layer. For electrical measurement, you are right, because actually it's true that the amorphous silicon, it has almost quite low conductive. But the problem is that if you illuminate this cell, you would generate the carriers in the whole wafer, and the charge carriers which are generated in the distance of the diffusion length, they would participate in the current also. And this diffusion length for solar cells of a high efficiency would be quite large. It's up to a few millimeters, or even up to centimeters. It's crazy, but up to centimeters. And actually, you see, you can get a huge additional current, which comes from incorrect determination of the area. It's some limited example, but I mean, there are a lot of cases when you think that your photoactive area is just some small area, but in reality you have a generation outside this area. The best solution to avoid this problem is to use some kind of aperture with the area which corresponds to this to a photoactive area. In this case, if you for example, use some sheet of don't know, of metal or even paper, but which doesn't, which is not transparent, with some true which correspond to the area of your of the photoactive area you thought is, and in this case there is no problem with the surface determination, because you already determined the surface of the eliminated area. There could be also some kind of errors if you try to calculate the area of very low dimension objects, for example, some nanowires, some viscous, and etc. You can see that your photoactive areas of a single viscous is only the diameter, and you don't take into account any diffused light, etc. I mean, in this case, the best solution is to use this kind of aperture. And actually there is some requirement to avoid this problem of this area determination, that for non-concentrated measurements, the area of solar cell should be at least 1 square centimeter for certified measurements. I mean, if you want to publish your record, at least for non-concentrated solar cell, at least you have to prepare 1 square centimeter solar cell. I mean, it's a requirement. So another thing, it's a error when you try to determine fill factor by different location of the probes. As I already told, it's not maybe a real error. I mean, if you know the rules, you can choose the correct position of the probes, but you can get some difference in the measurement for the different cells. So you have to really realize the dependence of fill factor on the position of the probes. If you have some problem with the sheet resistance of your grid or your TCO layer. And the next, which seems not really obvious at all, it's a problem which is related to the influence of the reflectance. Actually, it's quite, I would say, fine thing, because normally the measurement table, it's made of some metal, some reflecting material. So I mean, normally it's made of material which has a good electrical contact with the solar cell, and in most cases it has good reflection. For example, gold, you see it reflects very nice. Then if you calibrate your system with, for example, a large reference solar cell which has a black surface with almost no reflection, and for example we can cover the whole table, we calibrate the intensity, and then we place small solar cell with the free surface of this table. And in this case you see there are a lot of places which can reflect the light. The light can go to the simulator and come back with some additional intensity. Of course, it's a few % of intensity, but it could be enough to get some yellow in the intensity. It's things which is really, I would say, unpredictable for the most cases, because you can think that it could be negligible. But actually, it's not the case. You have to really care about it. If you want to provide a precise measurement, you have to think about this reflectance, influence of the reflectance. So the real cases when for the different covering of this reflected table, you can get different results. So it's crazy. So for this part, concerning the IVQ measurements, it's all. And I will start another part, the last one. It's, opening. Once we have delay, I think I have to think about. Try really change the slide, but it's don't see the. messages are saved. So I'll try to use source. Just copied it, but it's crazy. The new version was not. Okay. The last topic is really related to some specific part of thin film solar cells, mainly based on amorphous hydrogenated silicon. But it could be very interesting to compare with some modern type of solar cells, like a perovskite solar cells, and you can compare the difference and you can get your conclusion. So, concerning the thin film technology related to amorphous hydrogenated and related materials, first of all, we have to say a few words about the Stable-Wronski effect, which was observed for materials. This effect is related only for the materials. It's nothing to do with the... So it is related to the solar cell characteristic, but I mean, it is... When we are speaking about Stable-Wronski effect, it's mainly the changing of the properties of the material, electrical properties. So what happened? Here is the famous diagram. When you have some conductivity of amorphous hydrogenated silicon, so at the initial material you have just fabricated, you have this initial point at the dark. So it's a dark conductivity. Then you apply some light and you get photoconductivity. So it's normal, it's related to really nice photoconductivity. But then it was observed that the value of the photoconductivity decreases with time. So you have elimination and photoconductivity decreased. Actually, it is saturated, but have observed some kind of decrease. And then when you switch off the light and try to measure the dark conductivity, you can see that the dark conductivity, a few orders of magnitude lower. It's really seems to be strange behavior. So if you perform some intermediate measurement, you can see the drastic decrease of the dark conductivity. Then it's saturated approximately like for the photoconductivity. And actually, this process is not stable. I mean, this is a so-called metastable state. So it means that we can go back by annealing of this solar cell at vacuum or even in air at 150 to 150 degrees, and then we can go to the initial point and repeat it again and again. So it's really a metastable state. So if you have a look to the decrease of the photoconductivity, so first of all you have to think about the photoconductivity that is corresponds to the so-called mu-tau product, so the product of the mobility lifetime. So actually it should be generation rate also here, so it's not just it's a photoconductivity divided to the generation, so it's normalized to the flux. So the decrease of the photoconductivity means, so this is the charge of the unit of the electron. So this decrease is related to the decrease of this nu tau product. Actually, the both decrease of the mobility and lifetime related to increase of the normally defect density. It's obvious. So you have a high concentration of the defects, you have a low mobility or low lifetime. And actually, if you have a look to the dark photoconductivity, it's a little bit specific case for amorphous hydrogenated silicon. So any conductivity could be expressed by this expression, but concerning the amorphous silicon, the concentration of the charge carriers actually depends exponentially on temperature. It is also related to the higher defect density of states, which fix the position of the Fermi level. As I told before, the change of, for example, VOC with temperature is related to the statistical shift of the Fermi level, because we have a concentration of the charge carriers, I mean, for the dark condition, the charge carriers is almost unchanged with temperature. It is related to the doping, and then you have a shift of the Fermi level. Here it's a different thing. So we have a fixed position of the Fermi level due to the so-called pinning effect, due to the defects. So it's really fixed. And then if you change the temperature, the concentration of the charge carriers would change exponentially. And here, if you trust the Arrhenius plot, so it's inverse temperature, it's logarithmic of the conductivity. So we can get this Arrhenius with some activation energy, which corresponds to the position of the Fermi level. And if you have a look, not only the absolute value of the dark conductivity changed, but also the temperature dependence changed. So this so-called activation energy is changed. So it means that we have a deeper position of the Fermi level. So actually it also corresponds to the high defect density. So it means actually, if you have a precise look, in this case, it's real in the mid gap. So it corresponds to the pinning of the Fermi level in the mid gap. And it's some kind of another confirmation that we have a higher density of the defects due to the light soaking. So we can think that it's really a problem, and it was so really discussed disadvantage of amorphous hydrogenated silicon, that it's a nice material, it's very cheap, we can get some I would say considerable efficiency, but the problem is that it's unstable material. But actually now, if you have a look to the properties of the solar cell, to the efficiency, so we can see that it has this behavior. So I mean, we have a more or less drastic decrease of the solar cell efficiency for the first time, and then we have some kind of stabilization. So it is self-saturated process, as people told. Actually, there are different approach to this effect, but so to different approach to describe this effect, but the main thing you have to know that it's really saturated. If you plot the scale, the logarithmic scale of the time, so you can see this as some kind of slope, but the logarithmic scale of time, it means that first you have a seconds, minutes, hours, days, years, then 10 years, centuries, and then thousands. So I mean that here you have so slow changes, then you can really neglect it, and can just care about these first fast changes, and then say that it's stable. So if you have a look to the IV curve, so you can see that first of all we have a decrease in the fill factor, and then we have a small decrease of the short circuit current. So we will see changes is not so important. And actually, as I told, there is some discussion, still some discussion about the mechanism of this effect. But was well known that we really need some recombination process to provide this degradation. So it means that the maximum degradation occurs when we are in an open circuit condition, or you see in the maximum power it's not so far. Lower degradation if you are in the short circuit current, and the minimum degradation if you apply some reverse bias. So actually it corresponds to really dependence of on a recombination process. So you can provide this equivalent of the changes, equivalent of light-induced degradation, just by the current in the DAC. So if you are in some direct bias, you provide some current and you get some recombination, and then it would be the similar effect. So if you have a look to the dependence of thickness, it's also another important thing which has some more or less a general rule that you have a higher degradation for the higher thickness. Actually, the same thing for the degradation of some 3-5 solar cells under high radiation in the space condition. You need this thinner solar cell to get lower degradation. And for example, you can see to the dynamic of two solar cells. This is a thinner one. It has a lower initial point, but has a higher light socket value. The same, the same curve, but with a different result for the solar cell with a higher thickness of the active layer. We have a higher initial point, and due to the more pronounced degradation of the high thickness, we have a lower light soaking value of the efficiency. So there is some engineering approach to reduce this effect, and actually you can see here is example of a 400 nanometer thickness. Just for your notice, for double junction amorphous hydrogenated microcrystalline solar cells, the thickness of eye layer was about 200 nanometers. So you see it's even less then for this value. And concerning this this drop of the efficiency, actually it's in a range of 10 to the 20-25% decrease. And again, it's quite important that it's stabilized value. It can even a little bit increase due to the heating by the sun, but so we see that it's not factor of 2, 3, something, etc. And it's saturated process. So if you compare with the perovskite solar cell, you can see the difference. And actually, this effect is related only to the light soaking. I mean, it's light-induced degradation. It's you can compare the different type of degradation, so you can find some degradation of the contacts or some TCOLS. It's nothing to do with this. I mean, this is especially light-soaking degradation. And for this effect, there was some kind of standard condition to test it. Because as you see, there is a difference between initial and stabilized values, and any producer of this thin film models have to specify the value of this so-called light socket value, and there is some conditions that have to stabilize to get this light socket value. After 1000 hours of illumination, so it corresponds approximately to 40 days. It's really a long period, and you have to use some intensity of 1 kilowatt per square meter. But actually, there is no requirement for the strict spectrum match. It should be some kind of equivalent which corresponds to this short circuit current, which is related to 1 kilowatt per square meter. And actually, because the only one thing we have to reproduce is the recombination effect. The main thing that have to do it during 1000 hours. It's a really long period. So if you want to perform the measurement for the large models, you see it's crazy thing. Try to eliminate the large model during 40 days. As I told you, for the IVQ measurements of the models, normally the flash simulator are used. So to eliminate during the 1000 hours, it's crazy. But what normally to do? Just separate the model by some small so-called mini modules from different parts of the model. For example, you can take one from the corner, from the border, from the center, just to get some information about the degradation of each part of the model. Normally it's something like a small mini model, like a 10 by 10 square centimeter, and put it in the special light soaking system. You can see it's already quite a large scale device. So we have a lighting system, because actually it should provide the light during 40 days. It's really, and so we put the samples here. So up to 36 millivolts. I mean, this is some kind of example from a standard Oerlikon line. And you provide the intensity of 1 kilowatt per square meter with temperature control. So you put the sample and start the degradation. And of course, you perform some intermediate measurements to get this cube. It's not only first and last measurement. So normally you can take your cell and make some measurement, some intermediate measurement, and then to do it again. And you can get this nice cube. So if you have a more, let's say, modest budget, or you have no reason to make a large model measurements, you can do it yourself, some small system to provide this light soaking, because there is no strict requirement about the spectrum. So you can use, for example, halogen lamp. The only one requirement that it should work during 1000 hours. So you have to think about some safety control and the appropriate condition, I mean, of this power of this lamp, because it's lifetime. It's already, for example, for xenon lamp, the lifetime corresponds approximately the same value. It's 1500 hours. So it's crazy to use the xenon lamp for this light-induced degradation. So it's why you have just to get some illumination with the equivalent intensity. You can control the radiation, and it's okay.